now we're in the second case, linear equation where where n is equal to 1. So the interpolation polynomial is written in the form this one. Okay. So you can replace a1 with p of 0. Now given at least 2 data points, so we can get a0 and a1. So if you understand this equation, I think this one is very easy. Which is point equation. We have described previously. And then this one here, you can see this is like a line. Okay, so a1 is actually the slope of the line. So okay, to understand it further, so we have 2 points, 3 and 5, and then 2 and 4. Then we have PO a1. So actually you get it's like the slope of the line here. Okay, so as I said, a1 is like slope of the line, and then a of 0. Okay, so it's expressed with this one. So first p of 0 is equal to 1, and then p1 is equal to 2 plus x. So because first we deal first with one data point and then the second data point. So the function is a linear, 2 plus x. So the coefficient is 5 and is equal to 1. But in numerical methods, we don't do something like this. So we follow the recursive system, but in a reverse manner. So this is how we do it. Okay, so we are forcing the polynomial function to pass through each data point. So we have 2 data points here. Okay, first you assign y of 0 with a of 0. So basically we have 5. Okay, from the second point. From the first point, y of 0, this is equal to 5. And then for a1, so delta y1 is equal to, okay, as I said, it's like a slope of the line. Okay, the delta y1. So given the values here, okay, and with the formula, you get this equals 1. So which is the same as the previous here and this one. So if you compare the two processes, you can see that this one is very easy, and this can be repeated for not only n is equal to 1, but n as many as you want. Okay, so therefore the computer can easily do that. Okay, so then we can use the following formula to get the a using the code numerically. We can solve it numerically. So with the given function points 3, 5, and 2, 4. Okay, so we encoded here as an NP array. We can get a. Before we run this, we should run the previous code here. So import the library, and then this is a user-defined function where this function will return the coefficients. Okay, so as you can see here, this is the general formulation, which is this one here, and this delta to the n yn is this general equation. Okay, so we know that that's equivalent to a of any coefficient a of n, and then the n determines the degree of the polynomial. So when we run this, we have the function already, and then this one, okay, 5 and 1, which is the same as the previous 5 and 1, meaning we have the coefficients a of 0, which is 5, a of 1 is equal to 1. Now that's it. We were able to get the coefficients a. Okay, now given the coefficients and the x data, we can actually predict any y given any x. Okay, so that's what we have discussed in the introduction. So once we have data, we can actually predict whatever x values. Okay, so we have this function eval poly, given the coefficients derived from the previous one here, and then the x data, and then also the given x. So whatever x you want to predict. So this one is the data, and this one is, for example, whatever your desired value that you want to predict. Okay, so here you can see, okay, this is the original function p. So from the, if you look at again this reverse engineering, this is the original one. So recursive function. Okay, so actually this is from the general formulation, a of n plus this one here. Okay, so go to that eval poly. So you see here, okay, the previous p. So here is the previous p, and then this is the new p, and there's a loop. Okay, so we run this one, and here we want to predict what is the prediction y equivalent of x from the range 0 to 10 with a step of 0.25. Okay, meaning 0, 0.25, 0.5 up to 10 with that interval 0.25. So you want to predict y, okay, from that given x, and then we have the original x data. You look at the x data, okay, so 3 and 2, then we have the y data 5, 4. Okay, but we don't input the y data because we already have a coefficients. So then we can predict, no? So this is a function that gives us the y for x. Okay, so you can see here. Okay, so it's if you want to be sure with your answer, you can actually plot this one. Okay, so how to plot this? Okay, so you see, first we have these 2 points. This is actually the x data. Sorry, this is the x data and the y data. So if you can remember, we have 3, 5, and then 2, 4. 2, 4, then this one is 3, 5. Then this line here, okay, follows the y prediction and the x. You can see that it follows that it passes through the 2 points. Okay, these 2 points, so the line passes through this one. Okay, so this is interpolation because we are forcing a function to pass through the 2 points. Okay, so we know also in trigonometry that given 2 points you can construct a line. Okay, so that's why we call this one case number 2 linear equation. Okay, with the first degree. Okay, you can actually see the points instead of a line. You can see the points here. Okay, so these are the prediction. Okay, given the x. The x is from 0 to 10 with an interval of 0.25. Okay, so you see, given only 2 points, you can construct a line.